Okay, we're rolling. We're on 7.6, and here's the lesson for 7.6. If you have two different equations, we'll call that a system of equations, and I should say a system of linear equations, I should maybe add to that in two variables. Obviously, if I had more than two variables, more than just x and y, what if I had x, y, and z? Well, I couldn't graph them this way anyway. I'd have to have another axis coming in and out of the page for the z-axis. And then it's like, well, what if there's four variables? Well, then you have to imagine four-dimensional space. Good luck with that. Mathematicians and physicists especially do that all the time. There's a perfectly valid theory in physics that thinks space might be 22-dimensional in reality. So try to get your head around that. Anyway, as long as we only have two variables, we can graph them on an XY grid. And three things can happen when you have two equations and two unknowns. You can have one solution, which basically means one of the lines goes one way, and one of the lines goes another way, and they meet in one place, right? But what if they don't meet at all? Even if you drew this plane of existence here, this xy coordinate infinitely big, it is possible you could have zero solutions. What do you call lines that never meet anywhere? Yeah, we learned that in our last unit, right? The lines could be parallel. And this is me trying my best to draw two lines that are parallel. Okay, let's add some words to these situations. We have some room at the bottom here. Under one solution, here, let me divvy this up a bit. Under one solution, you'd say this happens when the two lines have different, finish my sentence for me. What has to be different about them for them to meet somewhere? Ooh. I thought that was an easy question. I got you stumped. Guys at home want to play? Finish my sentence. You will get one solution. The lines will meet somewhere. That's the word I'm looking for. They have different slopes. As long as their slopes are different, they have to meet someplace. Obviously, I get zero solutions when the two lines are parallel, which means, of course, they have the same slope. Nothing else about them has to be the same, right? They can have different x and y intercepts, like these guys here have different x and y intercepts, obviously. But if they have the same slope, they will never, ever meet, no matter how long you draw them, no matter how big the plane. You would say that there is zero solutions to that system because those two lines never cross anywhere. Now, this one's kind of strange to think about, but the third situation is you could have infinite solutions. How on earth would you have infinite solutions? What if you draw one of the lines, and then when you work out the equation and draw the other one, it's the exact same line? Remember what I mean by solutions? Solutions means where do the lines meet? Well, the two lines meet everywhere because they're the same line. So that's an infinite number of points where they meet. So I will describe this as when the two lines are, I'll use a fancy word, coincident. In other words, they are the same equation when simplified. For this one, I'll actually show you an example. Like, for example, if I had the equation x plus y equals 3, and I had the equation 2x plus 2y equals 6, you might look at that and go, oh, there's two different equations. Look at them. They look very different. No, they're not. if you divide the second equation, all three of its terms by 2, you simplify it to be the first equation. In much the same way that the fraction 1/2 and 2/4 are the exact same fraction, right? They're the same amount of pizza, just different size slices, but it's still the same amount. Same idea here mathematically. Those two equations are exactly the same. And certainly when you graph them, they're the same line. So if you had a system of equations where those were your two equations and you asked, what's the solution? Well, remember you're asking the question, what point do they meet at? Well, there's infinite points that they meet because one of them's right on top of the other. So let's do some examples here. We don't have to graph them all. Our algebra can tell us when we have each situation. For example, determine the number of solutions for this system of equations. Well, if I rewrite this one into the form y equals mx plus b, I get y equals negative x plus 3, which means it has a slope of -1. For this equation, if I rewrite it into the form y equals mx plus b, okay, well, I'll move the negative 2x to the other side by adding. Then I'll divide both sides of the equation by -1. And this one has a slope of -2. Therefore, this system has one solution. Why? Because the slopes are different. Give you a sec to catch up to me. All right, exemple 2. Determine the number of solutions for the following system of equations. Let's get the screen a little bigger here. There we go. So determine the number of solutions. So I'm going to do the same thing here. Oh, actually, no, I'm not. I'm going to notice something. You know what I notice here? If I take this equation and I multiply it by -2, look what happens. -2 times -2x is 4x. -2 times -3y is plus 6y. And -2 times 5 is -10. Therefore, there's infinite solutions. And if you want to say why, because the two equations are equivalent. That's the ugliest Q I ever made. I'm going to fix that. Equivalent, which means, of course, same line. If you tried graphing those two lines, they'd be the same line. So where do they meet? Everywhere they are, they meet. Well, those of you who are good with pattern recognition skills probably can tell where the next example is going to go. The first one had one solution. This one had as many solutions as you could ever want, infinity. Guess how many solutions example 3 is going to have? It's going to have 0, but let's see if we can see why. Well, let's see. This one's a little harder to parse. I'm going to try to actually do my algebra the way I've been doing algebra. I'm going to actually try to solve this system of equations. Now, obviously, if I was really, really good at this stuff, like had been doing it for 30-something years, like some old man or something, I could probably just look at them and go, you know what, I can see already they have the same slope. And there might be some of you out there that go, oh yeah, I can in my head very quickly shuffle this 2 to the other side of the equation, divide it by -4, and -2 divided by -4 is a half. That's the same thing I'm going to get when I divide this 3 by this 6. I'm going to get a half. So there's probably people who just, same as I was able to kind of look at that and go, oh, all I got to do is double and make that the opposite, and boom, it's the same equation. There's probably people with the same, what's the word I'm looking for, recognition skills, who can just go, oh yeah, definitely those both have a slope of a half. Let's get on with life. Those are parallel lines. They have no solutions. But they won't always be obvious to you. So what happens to you algebraically if you try to solve a system of equations and they don't actually meet anywhere? Watch this. Okay, so we're going to just play dumb here. No, we think we can solve this. So I'm going to maybe divide, no, maybe not divide. How about I'll times this equation here by 3, so that makes this a 6x. And then I'll times this, oh, I shouldn't use an x for multiplying. Bleh. There we go, 3. Then I'll times this equation by 2. You get where I'm going here, right? Then both of my leading terms will be 6x, and then I can subtract them and eliminate x. That's my plan. So here's my plan in action. 3 times 2x is 6x. 3 times negative 4 is negative 12. 3 times negative 1 is negative 3. Okay, my plan in action, part 2. 2 times the second one. Well, 2 times 3x is 6x. 2 times negative 6 is negative 12. And 2 times 2 is 4. Now I'm going to do what my plan was from the beginning. I'm going to subtract the equations from each other. And my plan was to eliminate x. And I did. 6x minus 6x is nothing. But hold on. Houston, we have a problem. What happens to y's? Well, they get eliminated too. What's negative 12 minus negative 12? So what happens on the other side of the equation? Well, negative 3 minus 4 is negative 7. Okay, last time I checked, 0 and negative 7 weren't the same number, but according to this algebra, they have to equal each other. This is your equation telling you, your system of equations, telling you that there's no solution possible algebraically because they don't meet anywhere. I end up at a statement that is ridiculous. You can say it two ways. You can say either, no matter what I do, I can't eliminate just one variable. I end up eliminating them both. Or you can say, when I try to eliminate the variables, I end up with something ridiculous, like 0 equals negative 7. Either way you think about it, this tells you that the system has no solutions. And again, alternate strategy could be, I could have just taken the two equations and drawn them badly. Sorry, hang on. Could have just taken the equations and then rearranged them. That'd be y equals 1/2 x plus a quarter. And then take the second equation, 3x minus 6y equals 2, and rearranged it, and I'd get y equals 1/2 x minus a third. And even though they have different y-intercepts, look at that, they have the same slope. What does that mean? They're parallel. They wouldn't cross no matter how big you drew them. Okay? So that's what's going on. If you want, you don't have to write this down, but if you want, here's another way you can think about it. When I was sitting here at this step here, again, don't write this down. This is just kind of thinking theoretically. And you were minusing here. You know what you could have done? Obviously, those guys cancel, but so do these guys. But you could think about it a different way. You could say negative 12y minus negative 12y is 0 y's. And then, what is always the last step of algebra when you get to here? You'd have to get rid of this coefficient by dividing both sides by that coefficient, right? See the problem? What's the unbreakable rule of all of math? You can't divide by 0, right? So no solution's possible. Just for fun, let's go back to example 2 for a second. What if I hadn't noticed that these two equations were in fact exactly the same? Or, okay, alternate reality. Again, you don't have to write this down. But suppose I'd have taken the first equation, and instead of noticing that the second equation, if I multiplied it by negative 2, would make the exact same equation, what if I'd have just saw the 4 and the negative 2, and I wasn't thinking very hard, and I wasn't being very good at noticing things? What if I'd have just doubled this equation thinking, oh good, that'll be 4x and negative 4x, and when I add the equations together, that'll eliminate x. Well, notice I would have had, okay, so original equation was, what was it? Negative 2x minus 3y equals 5, right? That was the equation, wasn't it? Yeah. Okay, so what if I'd have just left this equation alone, and I'd have plugged, again, times this by 2, and got negative 4x, And I didn't notice until I started working with it that, oh, hold on. Both of my equations are, or sorry, both of my equations, both of my variables are about to eliminate. 4 add negative 4 is 0, 6y add negative 6y is 0. I get 0 equals, but notice this one's different than the other example. The other example I had 0 equals negative 7, which is ridiculous. 0 is not negative 7. But look what I get here. What's negative 10 plus 10? Now this certainly doesn't help me figure out what x and y are, because I can't, because there's infinite pairs of numbers it could be. But it's not wrong either. 0 does equal 0. So there's a very subtle difference between a system of equations that has no solution because there's infinite pairs of numbers that work versus a pair where no possible numbers could work. And your algebra knows the difference. You either get something goofy, like 0 equals something that isn't 0, or you might just eliminate both equations at the same time altogether, including the constant, and get 0 equals 0, which, while again not helping you solve the equations, isn't wrong. 0 does equal 0. All right. This is deep stuff. Not necessarily tough to do, but you have to really understand things well to be able to think about them. Any questions? I saw someone with a hand up a second ago. You figured it out? Okay. Guys at home, you can play too. Any questions? All right. Last example. This is kind of a fun question. Suppose I have the equation y equals 6x plus 3. Give me another linear equation so that you'll get exactly one solution. Now, this is one of those, what you'd call in math, an open response question, right? Everybody could have a different answer. But how do I know you're right? Well, I would look at your equation, and basically, I couldn't mark you wrong unless that number was a 6, right? So this could be any number other than 6. And then for sure, they have different slopes. They'd meet somewhere. Sometimes I like to play with it. What if it was 6.000000001? Well, I might have to draw a heck of a long graph, a heck of a huge piece of paper, but eventually those lines would cross someplace, right? But if it's exactly 6, never. Does it matter at all what this number is? Nope. Could be anything you like. But if this number's 6, you have failed the task because there wouldn't be one solution, there'd be 0. How do I make it so there's no solution? No solution means that they have the same slope, so this number has to be 6. But then what about this number? What's the only way you could be wrong? If you put it as a 3, because then it would have infinite solutions. So this has to be a 6, but this has to be anything other than 3. And then this guy, how would you make me an equation based on this that you know is in reality the same equation? It just might fool me by looking different. Well, you could, for example, times everything in this equation by 2. And you could or times everything in this equation by -7. Etc., 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 right? Basically, you just have to make me any equation that simplifies to y equals 6x plus 3. And that's it. There's our systems of equations. The reason they make you learn this is because as you start using algebra to apply algebraic thinking to things in the real world to try to solve them, every once in a while, you'll think that you've made 2 different equations and you're about to solve them, and you haven't. You accidentally just interpreted the givens in such a way that you made the same equation twice, and you'll really quickly figure out that, oh, that doesn't help me solve the equation. That puts me into this category over here. Or you might have a system that you think has a solution and doesn't, which means that this will happen to you. So you need to be able to recognize those two situations. When there's no solution versus when there's no solution, but that's because there's no single solution. It's the same equation twice. There's infinite solutions. Any questions? All right, told you that was a short lesson. That's it. Let's do a couple ACCs. Now take out the other book. There you go. All right, let's do some ACCs. What are we going to do? We're going to do the other 4.21. Here it is, right? We left off, here's where we left off, right? We did, or sorry, I meant 7.4. We did this one last time. So this time we'll do this one. And then we haven't done an ACC on elimination yet. So let's do those two questions on 7.4 and this one question on 7.5. So there we go, 3 questions. Can you do, are they in the same order in your book that they are here? Is it 7.4 for a second time? And then 7.5 next? Yep, okay, good. So there you go. Can you guys do that? I'll pause the video. I'll keep recording the video. Guys who are watching the video, if you only checked in just to see the lesson, you can shut it off now. We'll just do these. But if you came in to see how the ACCs get solved, stick around. But I'll pause the video while people work on the ACCs. So pause your video at home and try these 2 ACCs on your mark, set, go. Okay, we're rolling again. So let's go over these. So 7.4, we have to use substitution. To me, the logical way to approach this one is, since this x is already without a coefficient, I mean it's got a 1 in front of it, I can just quickly move the 4y to the other side by addition, and then boom, I'm ready to plug that in. Okay, so x is 4y plus 16, so instead of 3 times x, I have 3 times 4y plus 16 plus 4y equals 0. And now I only have one variable, so I have 12y plus, what's 3 times 16? Is that 48? I think that's 48. Stop me if I goof that up. And 12y's plus 4y's is 16y's. I'll minus 48 from both sides, and y is equal to negative 3. And then since x is 4y plus 16, x is 4 times negative 3 plus 16, which means that x is negative 12 plus 16, which means x is 4. So my solution is 4 comma negative 3. Okay, you could do a verify if you want. Oh, did I do something wrong? I think I am, aren't I? Yep, we're recording. Thanks for reminding me though, but I remembered. Okay, any questions on number 1? All right, number 2. I think hopefully I've trained you to think, let's make the fractions go away in step 1, right? I mean, you can work with fractions if you want, but I'd rather not look at fractions. So I'm going to times this whole equation by 2. And I'm going to times this whole equation by 4. Don't forget to multiply the constants. It's super easy to forget that. All right, next. Since again, this is kind of already set up for x being just having a 1 as a coefficient, I'm going to rearrange the equation so that 2y, that's a sad y, let me make a better looking y. 2y minus 1 is equal to x. So then in this equation, I can replace x with 2y minus 1. So 2y minus 1 plus 3y equals negative 12. Then distributive property. And then add like terms. Some people might notice that everything here divides by 3, but I'll keep you doing it the normal way. I'll add 3 to both sides of the equation, and I'll divide both sides of the equation by 9. Then the people who did a simplify by 3 here don't have to worry about it there. They've already got the final answer, but I have to notice that, oh yeah, 15 and 9 both have a 3 in them. Okay, did I goof something up? Yeah, for some reason, thank you very much. See, if I'd have done a verify, I'd have caught that. For some reason, my negative disappeared on me. That was just carelessness. Let's try that again. So 9y is equal to, oh, this isn't going to be an ugly fraction after all. It's going to be a nice negative 1. There we go. Thank you very much. Now, let's see, where can we plug that in? Oh, we can plug it in over here. 2y minus 1 equals x, so 2 times negative 1 minus 1 is equal to x. So that's negative 2 minus 1 is equal to x, so x is negative 3. So there's my solution. Negative 3 comma negative 1. You know what, since I did make a mistake, let's do a verifying this just to make sure. Let's plug it in to, let's plug it into the second one. 3/4 of negative 3 plus 3/4 of negative 1 has to equal negative 3. Now, I know what you're thinking. You're thinking, oh, let's multiply both sides of the equation by 4 so we don't have to work with fractions. You can't do that on a verify. On a verify, you have to simplify the left and simplify the right, and you're not allowed to do any operations to both sides at the same time. Otherwise, you're not really doing a verify. So keep that in mind. So this is actually negative 9/4 minus 1/4, and see, something's wrong. Negative 9, oh, minus 3/4. How about that? That's better. There is something wrong. Apparently, I think 3 times 1 is 1. Ugh. I need more coffee. Negative 9 minus 3 is negative 12, and yep, negative 12 over 4 is negative 3. We've got the right answer. That's probably what you guys had too. Am I correct? Okay, good. Last one. This one we have to do by elimination, and if I add or subtract them the way they are right now, I'm not going to eliminate anybody because nothing's the same. So I think I'll take the top equation, double it, and then subtract them. There might be somebody out there going, oh, I times the top equation by negative 2 so that I could add them. That's fine. You should get the same answer I'm about to get. It didn't matter. You be you. All right, so I've multiplied the top equation by 2, doubling it, then I'm going to subtract the bottom equation. 4 minus 4 is nothing. We've eliminated x. Careful here. Negative 6 minus negative 5 is negative 1. And 2 minus negative 3 is 5. Right? So then y, remember there's a negative 1 here, so I divide both sides of the equation by negative 1, and 1y is equal to negative 5. And the one drawback of elimination is nothing's nicely set up for you to just plug the y in without having to do a little bit of work. I'll take the one with the smaller numbers. 2 times x minus 3 times 5. Oh, so look at that. There's a mistake. Negative 5 is equal to 1. So 2x plus 15 is equal to 1. 2x is equal to negative 14. X is equal to negative 7. So my answer, as far as I think, is negative 7, negative 5. Let's plug it into the other equation just to be sure. So let's do a check. Does 4 times negative 7 minus 5 times negative 5 actually make negative 3? So we'll just do a quick check just to make sure. This is negative 28 plus 25, and yep, that checks. We got it. So if that was a test, did you get all the marks? All right, cool. All right, I'll take any requests if anybody's stuck on homework. I'll stop the video. That's all that I'm doing that's kind of new today. But if anybody has anything that they tried in the homework, guys at home, you can play too, and it didn't go the way you thought it should go, then we can go over it. Otherwise, you can just work on the assignment on the blog.